Hello guys, welcome back to my YouTube channel. Myself Girish BB. I'm studying in Sri Venkateshwara College of Engineering, Bangalore from the Department of Information Science and Engineering. Today we are going to discuss about the most important topic in data structure, that is dynamic hashing and leftist trees. The topic dynamic hashing leftist trees. First discuss about the introduction of dynamic hashing. The dynamic hashing is a technique employed in computer science and database management to handle hash collisions efficiently and dynamically adjust the size of hash tables based on the number of elements stored. The primary goal is to provide a flexible and adaptive mechanism for managing data in hash tables, as the number of elements and the distribution of hash table to change over time. Then hashing. The hashing is a fundamental concept in computer science and information retrieval, widely used to map data of arbitrary size to fixed size values, typically for the purpose of efficiently storing and retrieving data. The process involves using a hash function to generate a hash code or hash value and the input such as a key or a file. Then hashing function. A hash function is a mathematical algorithm that takes an input or message and produces a fixed size string of characters, which is typically a hash code or hash value. The output, known as the hash, is a digest that appears random and is unique to the input data. Then the purpose of hashing. Hashing is a commonly used for indexing and quickly retrieving data in data structures like hash tables. It provides a way to map data to a location in memory for efficient storage and retrieval. Then hash tables. Hash table is a data structure that uses hash functions to map keys to indices in an array. It provides constant time average case complexity for search, insertion and deletion operation when collision are effectively. Dynamic hashing using directories is a technique used in computer system to efficiently manage and retrieve data in a dynamic environment, where the size of the data set can change dynamically. This approach is often used in hash tables implementations to handle collision and according to the changed number of stored elements. Dynamic caching using directories. You can see the example for the dynamic caching. First one is 2-level tries on 4 pages. Second one is inserting C5 with overflow. And another example is inserting C1 with overflow. You can see the hashing directories here. Then analysis of directory dynamic hashing advantages. Dynamic adaptation. First one, the hash table dynamically adjusts its size, allowing it to handle varying numbers of elements efficiently. This adaptability is crucial in dynamic environments where the size of the dataset changes over time. Collision handling. The approach effectively manages collision by expanding the directory and redistributing keys. This helps in maintaining a balanced distribution, reducing the likelihood of collisions. Then extendable hashing. In extendable hashing, the hash table size is a power of 2. The directory contains pointer to buckets, and the number of bits used to index into the directory determines the number of buckets. When a collision occurs and the number of elements in a bucket exceeds a certain threshold, the directory is dynamically expanded and the hash function is modified. and the hash function is modified to accommodate the new directory size. The extendable hashing example, you can see, suppose that g equals 2 and bucket size equals 4. We have record with these keys and hash functions h of key equals key mod 64, like that. Key 208, h of key equals key mod 64 is 32. The bit pattern is 1 lakh. Linear hashing. Linear hashing dynamically adjusts the hash function to handle collision. Initially, a single bucket is used and the hash function is designed to distribute keys eventually. When a collision occurs, a new bucket is added and the hash function is modified to distribute keys between the old and new buckets. This process continues and the number of buckets increases as needed. Then directorless dynamic hashing. Directoryless dynamic hashing is a technique. It is used to dynamically manage the hash table without the need for a separate directory structure. You can see start of expansion 2, there are 4 pages, but insert the C5 pages, 10 overflows page 00 splits. Here in this approach, the hash table itself is used to manage the dynamic growth or shrinkage of the table, eliminating the need for an external directory to keep track of the structure. The leftist trees. The leftist trees means it is also known as the leftist heaps or binary trees that satisfy the leftist property. Leftist trees are a type of heap data structure similar to the binary heaps. You can see the leftist trees example like not leftist trees example, leftist tree example, and another one the leftist tree example. Similar to binary heaps but with some node modification that allow for efficient merging of two leftist trees, that is not leftist trees. The leftist property ensures that the left child of any node has a greater or equal rank, means the distance to the nearest external node, than its right child. Every subtree of a leftist tree is leftist comrade. Then the leftist trees. In the preceding section, we extended the definition of a priority queue by requiring that both delete max and delete minimum operations be permissible. In this section, we consider a different extension, like suppose that in addition to the normal priority queue operations, we are also required to support the operation of combine. This requires us to combine two priority queues into a single priority queue. One application for this, when this server for one property queue shuts down. At this time, it is necessary to combine its priority queue with that of a functioning server. Let n be the total number of elements in the two priority queues that are to be combined. Its heaps are used to represent priority queues. Then the combine operation takes 0 of time. Using a leftist tree, the combine operation as well as the normal priority queue operations take logarithmic time. The leftist trees. A leftist tree is a binary tree such that is, if it is not empty, then shortest left minus child of x greater than shortest right minus child of x. You can see the example extended binary trees corresponding. Then the advantages. Efficient merge operations. The first one, the merge operation in leftist trees is particularly efficient. This operation combines two leftist trees into a new leftist tree in 0 or log n time, where n is the number of elements in the larger tree. This is advantageous in scenarios where frequent merging or union operations are required, such as in priority queue implementations. Then, dynamic structure. Leftist trees dynamically adjust their structure during insertion and merges, allowing them to adapt to changing requirements. The structure of leftist tree ensures that the tree remains relatively balanced, resulting in the efficient operations despite dynamically changes. Then the last conclusion. Dynamic hashing and leftist trees offer effective solution for specific challenges in data management and heap structures, respectively. The dynamic hashing provides adaptability to changing datasets and addresses collisions issues, while the leftist trees excel in efficient merging operations and dynamic structure maintenance. The choice between these structures depends on the specific requirements and characteristics of the problem being addressed. Thank you for watching my video. Please do the like and subscribe and share.